Hey, it's Horner, and these are the next two questions. This is number 54, and we also are going to take a look at the next one, which is number 59. So 54, we've got that stone, and this is a good little picture to kind of show you what's going on. So stone 1 is released at rest, and we know that it's falling with a acceleration of 9.8 meters per second squared. So at 1 second, it's going 9.8, and then when it gets down to the bottom, we see that it takes almost 3 seconds for it to hit. Stone 2 is thrown, and when it's thrown, then it also still accelerates at the same rate, 9.8, but it already has an initial speed. And because of that initial speed, they both hit the water at the same time. They don't, however, hit with the same speed, because remember, this one had more speed than this one did when it was originally dropped. So the very first thing they want us to do is find that initial speed. So to do that, we need to just find out how long stone 1 was in the air. We know that the way we do that is we're going to take that height of 43.9 meters, and we're going to set that equal to the original speed of that stone. And so we're really just using delta y is equal to the original speed in the y times time, but this whole thing is 0 because there is no original speed for that first stone. And then we're going to add that 1/2 of gravity, 9.8 times time squared. And you can use 9.8 or 10. When we rearrange that equation, you'll see it's just the square root of 2 times 43.9 over 9.8, and you end up with almost 3 seconds for it to fall. For stone 2, it says another stone is thrown vertically down 1 second after the first one is dropped. So since we know how long it takes the first stone, we can just subtract that 1 second since we waited a second, and we say for the second stone, it takes 1.993 seconds. We can go back to our same equation again, and this time we're going to find out what is the speed, original speed of, and this is for that second stone. So same height, we've got our time, put it in both places, we've got 1/2 of 9.8, and notice everything is positive here. So we're defining down as positive, and that's why our value for gravity is positive 9.8 meters per second squared. Once we do that math, we end up with 12.3 meters per second downward, and that was the original speed. They want us to plot a velocity versus time graph for each stone, taking 0 time as the instant the first stone is released. So if we do that, you'll notice that when the second stone is released at 1 second, this stone is already going 9.8. And so if we go to 1 second and we plot the first stone, so the blue is stone 1, so this one is stone 1, and notice that it's going 9.8 at that time. So really our slope here is just 9.8 meters per second per second. This slope is also the same because it also only has gravity affecting it. So this is going to be stone number 2. However, we did throw it at 12.3, so we have to start the graph there, and then they both fall for almost 3 seconds, and that's where they stop falling. And so we have to stop the graph at that point. For the next question, this one is number 59. We have water dripping from the nozzle of a shower onto the floor 2 meters below, or 200 centimeters. The drops fall at regular equal intervals. And so the first drop strikes the floor at the instant the fourth drop begins to fall. When the first drop strikes the floor, how far below the nozzle are the second and third drops? So the picture here is probably the best way to kind of take a look at this. The first drop down here started at the top and it fell. It went to this first spot, and that would be at 1 second, and then 2 seconds. And then we all the way come down here, so that'd be that third second. Now, you'll notice that the distance between each drop is getting bigger. And that's because it has an original speed here and then speeds up and has a bigger speed here and then continues to accelerate on the way down. So we cover more delta y each time. So this is delta y, and this is our first delta y. So delta y1, delta y2, delta y3. So it's just the difference in the heights between each one. So how do you solve this one? Well, the first thing we need to do is we're going to take downward as positive. So again, on this one, we're not going to make downward negative. We're going to make it easy. So we're going to make down is positive and up would be negative. We don't have anything up, so we don't have to worry about it. We know our height is 200 centimeters or 2 meters, and we know gravity is positive 9.8 meters per second squared, because on the way down, we're going to speed up. We need to find the time for drop 1 to fall. And so we're going to say the height there, which is 2 meters, is equal to 1/2 of gravity times time squared. So if we rearrange this for time, you'll see that it takes a total of 0.639 seconds for drop 1 to fall. Now, I think earlier I had said something about 1, 2, 3, and that's just time 1, time 2, and time 3. So those times, that time 1, time 2, and time 3, are each represented by this funny symbol. So you could put anything in here. You could do X, but they like to do this funny looking symbol. We call it tau, and it just means this is the interval of time between the dots, between those drops. So if I know that it took 0.639 seconds, and we know that the drops fall at regular intervals, we just need to find that interval. So that's all that funny looking symbol is. We're going to take and we're going to say the problem says drop 1 lands at the instant drop 4 begins to fall. So we have drop 1 go down, drop 2, drop 3, and then drop 4 starts at the at that third time. It's not 3 seconds, and it's not the fourth time. It's 3 times the time that it took for that other drop to get to the ground. So how do we do this? We just say, well, that time interval between drops is equal to the total time divided by 3. Because if you notice, when this one's on the ground, we've got 1, 2, 3. And we're just going to take the total time and divide it by 3, and we get 0.2130. So the time between each one of these is 0.2130 seconds. So 0.2130 seconds and 0.2130 seconds. Remember, the scale here is for the distance. So the distance is delta y. These are the following. So 111 for the third time. The second time it travels 66.7, and then that first bit of time it travels 22.2, but each one of the times are the same. Now that we know that, we can look and see, and we can say, well, if this one left the nozzle at time 0, the time it took to fall was 3 times the interval, and that's 0.639. For the second drop, it'd be 2 times that interval, 0.4259. And for the third drop, it would be 2 times the interval. And then for the fourth drop, it just was released, so it hasn't really gone anywhere yet. So now that we need to go through and find the distance for those drops. So we know that for the second drop, we see that this is the second drop right here, and we want to know how far it's fallen. So we're going to take 1/2 of 9.8, and then we're going to take that, and we need to multiply that times the time that it's been in the air. And so basically we're just taking 0.2130 times 2. They rounded it a little less here, so anyway, you kind of get the drift there. And if you do your math, you get 0.889 meters, or 88.9 centimeters. So that's how far it has fallen. So that's the total of these two. And then the third drop would be this guy right here, and he's only fallen just the 22.2 centimeters. And that is how you go through and do that problem.